Okay, so we're taking a look at fins, conductive, convective systems, and in the last segment what we did is we came up with an expression for the temperature distribution along a fin. We had made a substitution of variables and we were expressing it in this theta of x, but what we said is the temperature distribution could be expressed as a linear combination of the solution that we came up with. And in order to solve for C1 and C2, we need boundary conditions. So that's what we're going to look at now. And just to refresh your memory, we had this as being the base temperature of the fin that we were looking at. And we made a bit of a simplifying assumption. We assumed that the cross-sectional area of the fin did not change with x, and so we were dealing with what we call a fin that has no taper, or it has uniform area. And the things that we were specifying, we specified the perimeter, so there would be some perimeter at a given location x. So let's say that is x, and what we're after here, one of the things that we're after is to know the temperature at that location, and then we're also going to try to come up with the heat flux. And the heat flux is going to be at the base because we want to know how much heat the fin is removing from the base. So we need the boundary conditions. What we're going to do, we're going to assume three idealized cases, and from that, I won't go through all the math, but I'll give you the results of each of the cases. And the results being the solution, basically determining what the boundary conditions would be, and then determining what the constants of integration would be, the C1 and C2. So we're going to take a look at three cases. Case one, that would be the case of a very long fin. So if you imagine we have a very, very long fin, not fin, and what will happen as the fin gets very, very long, eventually the temperature of the fin is going to become the same as the free stream temperature. So we can say temperature at this L being some very long distance, eventually we'll get to the free stream temperature. And with that, with our variable, theta at that L is then going to be equal to 0. So that's boundary condition scenario, or case one. Case two is a more realistic one because you'd never have a fin that long that it gets to the ambient temperature. Well, you could, but usually you wouldn't. Case two is finite length. And we're going to lose heat from the tip via convection. So this is the most realistic scenario because that is what actually happens. And if you imagine here we have our fin, and let's assume that it's round in cross section. So AC is the cross section as we come out along the length. What we're assuming is that we have Q coming in here, and then that's going to go into Q convective heat transfer. So let's try to express that and giving us a mathematical representation. So we have Newton's law of cooling on the end, HAC, because the area is not changing as we go along that length of the fin. And it will be the temperature at the end of the fin minus the fluid temperature that the fin is exposed to. And then on the right-hand side, we'll put Fourier's law. And we'll apply Fourier's law right at the end of the fin tip. So that is going to be dt dx evaluated at x equals L. So essentially, it's equating the slope. Because what's going to happen here is that cross-sectional area is going to cancel out. And what we end up with is the following. At x equals L, not 0. Okay, so that's finite length. We lose via convection at the tip. And case 3 is another one that's a little bit of an idealization. That would be the case where instead of having free convection at the tip, you put insulation there. And so there is no heat transfer from the tip. And if the tip is insulated, we know that when we look at the boundary conditions, we looked at this when we came up with the heat diffusion equation. If we have a case of insulation, that means that through Fourier's law, the slope of the temperature profile at that point is equal to 0. And therefore, writing that in terms of our variable theta, we get that. So those are the 3 different cases that we have: case 1, case 2, and case 3. So what you can do is you can take these and plug them into the solution that we had from the Finn equation. And there is one other boundary condition that I forgot to mention before we go to determining C1 and C2. Let me mention the other boundary condition. The other boundary condition is what is happening at the base of the fin. And if you recall from our schematic, we said the temperature at x equals 0 is equal to Tb for the base temperature. So we can write out a theta, a base at x equals 0 is Tb minus T infinity, or the free stream fluid temperature. So with that, what I'm now going to do, I'm not going to go through the math, but I'm going to give you the results in a table for all 3 cases: that of an infinitely long fin, that of convection from the tip, and that with an insulated tip. So let me write out all of those. And when I do that, I'm going to give you 2 values. One is going to be the temperature distribution, and the other is going to be the fin heat transfer rate, which will be evaluated at the base. It basically tells us Q leaving the base, and that gives us the amount of heat being removed from the surface. Okay, so those are the results that you get when you put in the boundary conditions and you solve for C1 and C2. And in here, we have a lot of hyperbolic sines, cosines, and tans. But recall theta was T minus T infinity. We said m squared was HP divided by KAC, so the cross-sectional area, convective heat transfer coefficient, perimeter and thermal conductivity of the fin. Theta B was equal to theta at 0, which is then the temperature of the base minus the free stream temperature. And the last thing, I haven't mentioned it yet, but you'll see in the table we have this M term that appears in the heat flux coming out of the base. M is defined in the following manner. Theta. So those are the different terms. This here on the left gives us the temperature profile in the fin, and this gives us the heat transfer that the fin is removing from the surface. And when you look at these, if you recall the long fin case, that wasn't really a physically realistic application. The convecting tip was the one that was very accurate, but when you look at the mathematical expression, it's rather complex, although in a computer it's not a big deal. And then finally, case 3, the insulating tip one. That is a rather simple solution. And so what we'll be doing in the next segment is comparing these 3 different solutions and seeing how well they compare for different types of applications for a given problem. So that is the Finn equation and solutions to 3 different cases. And like I said, in the next segment, we'll be plugging some numbers into these and taking a look at what the temperature